limits that don't exist. And I did exercises 60 and 61, and I'm going to continue now with exercise 62. Exercise 62, we are asked to investigate the limit as xy tends to 0, 0. Please keep quiet. Okay, does that limit exist? And if it does exist, what is the limit? Okay, if we draw a domain picture, now I know some people were confused by my domain picture yesterday because people thought I was drawing the surface xy squared over x squared plus y to the 4. I'm not drawing that at all. I'm only drawing the domain. And the domain is the xy plane except for the origin. And as well, it's so just like in our 2D picture, if you could please keep quiet. If you remember our 2D picture, I had an x equals a, and I said we could approach from two directions, from the left, from the right. If I just drew that real number line there, that would be equivalent to what I'm drawing over here, okay? It's the domain picture. I'm just drawing the domain. Okay, let me rub that out now. So I'm basically drawing the point of interest, which is the origin, and I'm talking about which curves, which paths I'm going to approach along. So the paths that we approached along in the previous two exercises were, let me use black instead, here we go, were the y-axis, in other words, x equals 0, the x-axis, in other words, y equals 0, and then I also went along the path y equals x for exercise 61. So let's try those for this exercise. Okay, approach 0, 0 along x equals 0, in other words, the y-axis. We'll have the limit as 0y tends to 0, 0 of 0 over y to the 4, which is just 0. Okay? So we're approaching along those black arrows that are above, that are vertical. Switch off this light. There we go, I think it's more visible now. Okay, so those are the black arrows along the y-axis. Let's try the little black arrows along the x-axis. Approach 0, 0 along y equals 0. And then we'll have the limit as x0 approaches 0, 0. So we are setting y equal to 0. We are not setting x equal to 0. We are allowing x to approach 0. Different thing. But it ends up not mattering because the limit of 0 is just 0 no matter what x is approaching. Okay, so far we have no disagreement. Let's try those oblique black arrows along the line y equals x. Approach 0, 0 along y equals x. We have the limit. Now I'm going to write x comma x tends to 0, 0, but you could have y comma y, or you could even have a comma a and replace x with a and y with a. It doesn't really matter. The idea is that your x and your y are the same, so give them the same letter and allow that letter to tend to 0, that unknown to tend to 0. So in my case, I'm calling everything x, so that's x cubed over x squared plus x to the 4. Okay, that's not terribly helpful. You could use L'Hopital's rule if you wanted to, because we have a numerator that tends to 0 and a denominator that tends to 0. But we don't need to use L'Hopital. We could use one of our little tricks that we use when we're solving limits. I'm going to divide top and bottom by x squared. I know that I can divide by x squared because I know x squared is not 0, because I know x is not equal to 0, it is approaching 0. So we don't need to worry about x being equal to 0. X approaching 0 is not a problem. X equal to 0 would be. Then we couldn't divide top and bottom by x squared. But I know that I can reliably say that x is not 0 because we're looking at the limit as x approaches 0. So x is by definition not 0. So I'm going to divide top and bottom by x squared. And now if I allow x to tend to 0, my numerator tends to 0, my denominator tends to 1, and altogether that entire quotient tends to 0. I'm not substituting in x equals 0. I'm looking to see what the numerator and denominator tend to. Numerators tending to 0, denominators tending to 1, the quotient will tend to 0. Limits are slippery things, but they're slippery things that you have to catch on and grab because, as I said yesterday, they are the absolute fundamental foundation on which all of calculus is built. Okay, but now you kind of give up in despair because, oh my goodness, we've tried so many options and we're getting 0 every time, and what we're trying to get is disagreement. We're trying to break this thing. We're trying to say, I found your weakness, the limit doesn't exist. So we need to try something else. What is that something else? Okay, I want to say the clue. Clue is not quite the right word. A suggestion can be seen in the actual algebraic structure of that function. xy squared over x squared plus y to the 4. We have a binomial in our denominator. It would be really nice if there wasn't a binomial, if we could somehow add those two terms together. So this is a sort of a trick that you can use in a lot of these. If you have two terms, if you have a binomial, see if you can somehow make it a monomial, a single term. So I'm going to do that by, currently I have x squared and I have y to the 4. I'm going to approach along the path x equals y squared, because that will turn that x squared into a y to the 4. So I'm going to do that. So what would that look like in my picture? X equals y to the 4, that would look... That would look like that if I were drawing it in the picture. Look, you don't need a domain picture. I like a domain picture because sometimes these problems that you get can be, these three that I'm working through are really pretty standard problems. Sometimes you can get ones that are trickier than these. And I find a domain picture very helpful in just keeping in my head where my paths are, and because sometimes even which quadrants the path is passing through can be important in how you structure your limit calculation. So I find a domain picture quite useful myself. Approach 0, 0 along x equals y squared. Now that path very strategically chosen to turn my binomial in my denominator into a single term, which is often a useful trick. So let's have a look. I'm replacing x with y squared. Y is staying y. Let me have a look. I've scrolled past it now. Let's have a look. It'll be y to the 4 at the top, won't it? Because it'll be y squared times y squared. It'll be y to the 4 plus y to the 4, and at last an end is in sight. Could you please keep quiet? Even if you are talking about maths, please keep quiet. I'm referring to those of you who are talking. And that is a half. The limit of a half is a half. Y can tend to 0, it can tend to infinity, it can tend to 2 pi, it can tend to whatever its little heart desires. The limit of a half is a half. Question? The domain picture. Cool, I can do that. I'll come back to this if you're still copying it down. Going back up to the domain picture. There we go. Oh, you're right, I did. Y squared. I beg your pardon, but the picture still applies. Thank you, thank you. Ah, now I'm in red. I don't want red, I want black. There, and there, and there. I apologize, I was already in my mind jumping ahead to when I was going to be squaring it. Thank you for fixing that. Question?
What if x is equals to y does not exist within our function, or an x is equal to y squared?
If for some reason, it would have to be a different function, but if for some reason the path that you're choosing is invalid for some reason within this, maybe your function is just not defined there, then you couldn't choose that as a path. So you can only choose paths that are legitimately within the domain of your function. So yes, and you do get funny ones like that, generally piecewise defined. I would recommend, I will draw to your attention, was it last year? Last year, first semester, class test 1 it must have been. I'm even going to go out on a limb here and say question 4. but it was this question about limits. Last year, first semester, class test 1, whichever question it was on limits and continuity, was a particularly tricky one. People bombed on it big time. And I found a domain picture really helped. If you look at my solutions, I think it was last year, I don't think it was the year before. It was a piecewise defined function where on half your domain, your surface looked like a certain thing, and on the other half of your domain, your surface looked completely different. And what you were doing was looking at the limit at the join, or at least at the potential join between those two bits. It was quite a tricky problem, and certainly the students of that semester found it a very hard problem. But if you can do that, without looking at the solutions, don't look at the solutions first. Try the problem first, draw a good domain picture, see if you can solve it, check the solutions, and if you manage to do that, then you know that you really understand this word question.
What should be our basis of drawing the domain picture?
You don't have to draw a domain picture. You don't have to. I find it helpful for tricky situations like the one I'm describing that was in that test, where certain paths are good ones to choose and others are not. And so I just like to also, when you get to exercise 65, which I'm going to ask you to do in a moment, you'll see that the point that xy is tending to is not 0, 0 like in all the preceding ones. It's the point 1, 2. So if you draw a domain picture and draw your point 1, 2, it keeps it very vivid in your mind that whatever paths you choose, for instance, that path along the x-axis and that path along the y-axis are useless paths. They don't pass through the point. And the paths have to pass through the point. So I like to draw a domain picture because it keeps my mind focused on which is the point my paths have to be passing through. And also sometimes you have some very odd functions where, I shouldn't say odd, I don't mean odd symmetry. You have some very strange and bizarre functions where if your path is on the right, you want to do a certain thing in your limit, where if your path is on the left, you want to do something different. And me personally, I find a domain picture kind of anchors me in what I'm doing, but it's not a necessary thing. I don't think certainly in the notes that I've ever seen the mainstream lecturers do, I haven't seen them really do it. In fact, drawing domain pictures is only something that I've started doing in the last couple of years, as I've found them increasingly useful. So, draw it, don't draw it, whatever you want. Okay, let me go back down to there. And the last little sentence, oops, a daisy, getting my colors wrong again. I want red. These results disagree. The limit does not exist. Okay, just let me fix that word results there, which came out a bit funny. These results disagree, something like that. The limit does not exist. You try exercises 63, 64, 65. I'm probably not going to give you enough time to do all three in the lecture now. What is it? 63, 64, 65. I'm telling you now, the limit does not exist in any of those three, but you try and prove it. Even if you're talking about maths, please keep quiet. It's a tricky section, all right? Limits that do exist, okay? What if the limit does exist? Okay? Please keep quiet. The paths of approach method will not work to prove that a limit exists. Let me actually write that down. The method of paths of approach does not work. I'm going to underline that. to prove that a limit does exist. Okay? Because what if you approach along one path and you get 0, another path you get 0, you try a third path you get 0, you try a fourth path you get 0, you start to think, good grief, I just can't find a disagreement. Another path, another path, another path, you get 0 every time. You can start to become suspicious that maybe the limit does exist, but it doesn't count as a proof. Because what if you just haven't been sneaky enough to find the path that'll just break the thing? You can never be sure. So this paths of approach method is perfect for finding limits that don't exist or for proving that limits don't exist, but it's useless for proving that limits do exist, because what if you just haven't looked hard enough for that one path that will do the trick? So in order to prove that a limit does exist, you need to use a completely different method, and what we use is the squeeze theorem. Everybody loves the squeeze theorem. Okay, all right, and here's the idea. Let me do a little bit of writing, maybe a bit of a picture, if I can think of a picture that'll work, and then I'll demonstrate with an example. If the limit does exist, and the limit as xy tends to AB of f of xy equals L, please keep quiet. Then it follows, always be a little bit suspicious when you see that. Doesn't really follow. Is it going to be as clear to me as it is to you? It follows that, I think you'll agree, the distance between f of xy and L can be made arbitrarily small as the distance between xy and AB becomes sufficiently small. Okay, it's in fact probably best demonstrated by actually harking back, because 3D pictures are trickier to draw. Let me demonstrate with a single variable function, and then we can step that up to a 2 variable function. Back in the day when you were drawing this sort of function, okay, in the left-hand picture the limit does exist. In both cases the actual function value does not. Okay, let me call that A, let me call that L, and then let me call these L and M. Okay, in the left-hand picture, as x tends to A, our function tends to L. Okay, and what that means is you can make your you can get a y value on your function as close as you want to little l, as long as you make x sufficiently close to A. So let's say L was 10. Okay? And A was 1. All right. Then we can find values of 10.1 and let's say 10.1. Can we find a point on our curve that has a y value of 10.1? Yes, we can, and it'll correspond to an x value quite close to A. Can we find a y value of 10.01? Yes, we can. We'll just have to choose x even closer to A. But we can basically make the distance between little l and any function value tiny, as long as we choose x sufficiently close to A. Because that's what it means for the limit to exist. Because the function actually goes there. In the picture on the right, you can't do that. You cannot make, let's say L is 10 again. Okay? Well, the 10.1 and the 10.01 on my picture is still fine. But what about 9.9? What if M is 9 and L is 10? There's nothing in between 9 and 10. So we cannot actually choose Y values arbitrarily close to L simply by choosing X closer and closer to A. There are some Y values that we just cannot get. No matter what we do to X, the limit does not exist. So there's something called epsilontics. It's epsilon delta expressions of mathematical concepts. And if you go digging down into the theoretical groundwork that underlies all your limit laws, you'll find these epsilon delta things. And the epsilons and deltas refer to very, very small distances, very, very small distances. And the whole idea behind limits is that if f tends to L as x tends to A, it means the distance between any f value, any function value in L, can be made arbitrarily small by simply choosing x sufficiently close to A. Okay, and then the same thing goes for two-dimensional functions, which is what I've written in the red there. You can find, if the limit truly does exist, it means that you can make the distance between your function value and the limit arbitrarily small by simply choosing points in your domain that are sufficiently close to AB. Okay, so what? Well, because we're talking about distances, it means, let me go back to red. So the distance modulus of f of xy minus L tends to 0 as xy tends to AB. Okay? That's me writing in symbols what I said in words. Whenever you have something minus something and you take the modulus of something minus something, what you're talking about is the distance between those two somethings. So the modulus of f minus L is the distance between f minus L, and we can make that distance arbitrarily small by simply choosing xy sufficiently close to AB. Okay, so what we do is we deal not so much with the function itself, but with the distance between the function and what we suspect its limit to be. Oops-a-daisy, sorry, that was accidental. I didn't realize I was that close to the edge of the page. Consider the example of f of xy equals 3x squared y over x squared plus y squared. Is that the example I want? I think it's the example I want. Yeah, exercise 70. Okay, I'm going to do a page jump now. Can I do that? Everybody jotted that down. That little distance formula is important. Okay. Oh yeah. There we go. It's at the top. So we want to look at the limit xy tends to 0, 0 of 3x squared y over x squared minus y squared. This is exercise 70. We want to see, does the limit exist? And if it does, what is the limit? Okay, so now I've said to a few of you that I'm going to give you a bit of a rule of thumb for going into a problem already being fairly strongly convinced whether it exists or not. It's a plus. Plus? It's a minus. It's a plus? It's a plus. Question? Is that what you were pointing out? Is that what you were pointing out? Thank you, thank you. And in fact, over there as well. Yes, I just can't copy properly. Okay, look at the exercises that we've already done, 60 through to 65. 65 is a bit trickier to see. But look at the degrees of the polynomials in the numerator and denominator. If the degree of the numerator and denominator are the same, there's a strong possibility your limit does not exist. If the degree of the polynomial, if the degrees of the different terms are a bit jumbled, and it's a bit hard to say which is bigger and which is smaller, there's also a strong possibility that the limit does not exist. If the degree of the polynomial in the numerator is greater than the degree of the polynomial in the denominator, chances are, unless there's something very strange going on, that your limit does exist. Okay, because it's like one of those L'Hopital situations where you have a numerator is trying to do one thing and a denominator is trying to do the opposite, and which one wins? Okay, but if you have a cubic at the top and a quadratic at the bottom, the cubic wins. A higher degree, yes, no, maths is very unfair. You cannot vote for the underdog because higher degree polynomials always beat lower degree polynomials. Exponentials beat everything. Everything beats logs. It's to do with rates of increase. It's to do with rate of increase. Which one ends up with the power? So if you look at exercise 60, it's quadratic over quadratic. 61, also quadratic over quadratic. 62, bit of a jumble. Cubic at the top, but quadratic and quartic at the bottom. You look at the terms separately. So it's a bit of a jumble. Hard to tell. Quadratic over quadratic in 63. Fifth degree over a combination of quadratic and whatever you'd call eighth octic in the denominator. And that sort of jumble where you can't really tell which ones, I mean, it looks like the denominator has the power, but there's actually a bit of a jumble. When you have that sort of situation, same over same, or a bit of a jumble, strong chance the limit does not exist. Try to break it. Try to find paths of approach where you get different results. But in the one I'm doing now, it's cubic over quadratic. I know that limit exists. I know it. I can do paths of approach, but I know I'm going to get 0 every time. I just am. The cubic's going to win. Question. The one I'm doing now. Even though the x is squared, let's say x and y were actually measuring something that had units, like centimeters. I'd have centimeters cubed in the top, and I'd have centimeters squared at the bottom. So think of it in terms of it like a unit measure, yeah. Like a, what do they call that? There's a word I'm looking for, but I've forgotten. But testing the units. Question. When the numerator is bigger than the denominator, then the numerator wins, and the numerator wants to go to 0, and the denominator saying no. The denominator saying I want to go to 0. So the numerator saying let's go small, the denominator saying let's go big, and it looks at first glance like there's a bit of a fight between the two, but it's an unequal fight. Numerator wins. Whole rational expression is going to go to 0. Yeah. Okay, all right, but let me demonstrate. We have 6 minutes, right. Sorry, that's my phone busy whistling over there. I should have put it on silent. Okay, consider, paths of approach. Suggest, it's just a suggestion, but it suggests, paths of approach suggests, plural, that the limit is 0. Okay, but you can kind of see that just with your eyes. You can see that given what I've just said about cubic over quadratic. Look, and sometimes we can chuck really strange functions at you with that rule of thumb. You've actually got nothing to go on. In which case, try the paths of approach first. If you look at it and you go, I actually don't have a clue whether it exists or not, first test to see whether it doesn't. Try some really obvious paths. See if you get a disagreement. If you don't, then say, well, perhaps it does exist. Let me try the squeeze theorem. Okay, all right. So consider the distance 3x squared y over x squared plus y squared minus 0. Okay, that 0 is this L. If we'd done the paths of approach and it seemed like our limit was 2 every time, then we would have put a minus 2 in there. Okay, all right. So what we're going to do is squeeze theorem. 3x squared y over x squared plus y squared minus 0 is greater than equal to something and smaller equal to something. If we knew how to work out the limit of the thing in the middle, we wouldn't be in the quandary that we're currently in. The whole thing we're trying to figure out is how do we work out the limit of the thing in the middle. So we're going to use squeeze theorem, where we're actually going to squeeze the limit that we want in between two other limits. All right. We get the left-hand one for free. Okay, because the thing in the middle is an absolute value, it's a distance, it's greater than 0. So we get the thing on the left free. Thing on the right, we have to construct. what do we put here? The thing that's in there has 3 requirements. Number 1, limit must be easy to work out. If it's not, we're missing the whole point of the squeeze theorem. Number 2, oh, that's supposed to say 2. Number 2, must be unarguably bigger than the middle thing. By the middle, I mean that absolute value thing in the middle. Okay? That's the bit where people fall down. And then let's say it is unarguably bigger. Let's say the limit is easy to work out. If the limit isn't 0, then there's no squeeze happening. Okay, the easiest way to achieve the middle thing is to actually, in place of that question mark, put something that looks very, very similar to the thing in the middle, but just has one thing that's been tweaked. So you've made the denominator a little bit different, but you have to put, because I could put like sine x in there, or e to the x, or something. How do I know whether it's bigger than the thing in the middle? The way you can know that it's bigger than the thing in the middle is by making it look almost like the twin of the thing in the middle, but there's just one little thing that's different. Question?
What do you mean by must be 0 for the squeeze?
Because we want squeeze theorem. So we want to say that the limit of the thing on the left is 0, and the limit of the thing on the right is 0, hence the limit of the thing in the middle must be 0, because it's being squeezed. So if the limit of the thing on the right wasn't 0, then we've probably written down a true statement, but it's not a helpful statement because there's no squeeze happening. Sometimes things in maths can be true, but not helpful. And we're trying to go for true and helpful. Okay, so in this particular example, I would recommend, let's have a look. Thing in the middle is a rational function, rational expression. So, it's got the sort of structure of a fraction. If you want to make a fraction bigger, you either make its denominator smaller or you make its numerator bigger. Those are the 2 ways of making a fraction bigger. So I want that red question mark to be bigger than the thing in the middle. So I'm going to do that by, I'm going to replace that x squared at the top with x squared plus y squared. That'll do the trick. That thing on the right there is unarguably bigger than the thing in the middle because I've taken the x squared factor and I've made it bigger. I for sure have made it bigger because I've added something positive. Okay? And of course, that thing on the right now simplifies to just 3y, or mod 3y. The limit, not limit, lim of 0 as xy tends to 0, 0 is 0, and so is the limit of modulus 3y. Therefore, by the squeeze theorem, also called the sandwich theorem, my first year textbook calls it the sandwich theorem. By the squeeze theorem, the limit of xy tends to 0, 0 of the thing in the middle which means, now remember I said if our limit hadn't been, if our paths of approach had all seemed to take us to 2, then instead of a minus 0 there we would have had a minus 2, but we still would have had this distance tending to 0, and then we would say limit of our actual function equals 0, and in my hypothetical example that would have been a 2. I'm actually going to, I will scroll back down to this. I just want to belabor something. Let me go up here. That over there is L. Okay, it's the thing that you suspect your limit to be. That thing over there is your L. That thing over there is your L. Question?
Is it important to have the minus 0 and flooding the whole way through?
No, you don't. Because it's just minus 0, so you can drop the minus 0 if you want. But I've got it there because it gets confusing, you see, because there's two important zeros in this problem. There's the 0 that you're trying to demonstrate that the distance tends to 0. That's your one important 0. The other important 0 is your L. It's your actual limit. Now your distance tending to 0, you're going to have in any problem like this. But in a slightly different problem, the 0 that's inside the absolute value could actually have been a different number. So I'm just trying to focus on that there's two zeros in this problem and they're different. Question?
Because we're using squeeze theorem, because we're using the distance, must we always make our upper limits of the squeeze theorem 0, 0?
Yes. And for the sake of the audio, in this context of using squeeze theorem, we're trying to show a distance tending to 0. Therefore, you want your left and your right-hand sides of your squeeze theorem expression to both tend to 0. Now, in other squeeze theorems that you may have seen back in first year, you may have been using squeeze theorem in a different context for a different purpose. Here, it's for a very specific purpose. We're interested in distance tending to 0. Right, we've gone over time, so I'm going to stop now.